Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In the previous lecture, I showed you that we're able to use state-of-the-art pre-built neural networks for image classification tasks very easily because they are already a part of Keras. We saw that we were able to use any of these models with just 2 lines of code. This is possible because, as we know, all machine learning interfaces are the same. So what haven't I told you yet? Well, suppose I have a totally new dataset that only consists of pictures of cats and dogs. So I don't need the 1000 classes that VGG gives me. I know for sure that if VGG outputs airplane, that the image is most definitely not an airplane because I don't have any airplanes in my dataset of cats and dogs. Or suppose I have images that belong to classes that VGG has never seen. For example, I want to classify between different types of exotic plants. Is there a way we can make use of VGG weights for these tasks? And the answer is, of course, yes. We learned this concept way back in Deep Learning Part 1, but it's worth reviewing now. Recall that a very useful way of thinking about a neural network is that it's a combination of 2 pieces. The first piece is a feature transformer. The final piece is a simple linear model that works on those features. So for classification, you could put a logistic regression on top of your feature transformer. For regression, you could put a linear regression on top of your feature transformer. And so the way to use VGG for new problems is to use all of VGG except for the last layer. That last layer is just a linear classifier designed to recognize whatever the 1000 classes of ImageNet are. So we can just throw that out. We want to make the assumption that the first part of VGG is a state-of-the-art feature transformer. It's been trained on millions of images after all. Sometimes people call this chopping off the head. Once we've removed the last layer of VGG, we can put on our own linear classifier and train it on our dataset. One ambiguity here is whether or not you should allow gradient descent to backpropagate through the VGG weights. If you recall from unsupervised deep learning, we call this fine-tuning. So whether you want to do this or not is up to you. It will probably lead to better results. The downside to this is that it will take longer, since you're effectively having to train the entire neural network. So, supposing that you decide not to fine-tune the VGG weights, the major benefit of this approach is that training is going to be very fast. You're basically only training a logistic regression model, which takes only seconds. But of course, you're not just restricted to these options. Yet another approach might be to first train the logistic model only, and then after that, fine-tune some more. Yet another approach might be to tack on a full multi-layer neural network instead of just a logistic regression. There are many possible variations. One thing that might help you understand this process a bit better is thinking of your data as a CSV file. We know that it's okay to store image data as a CSV. We've seen this in the past with the MNIST dataset. Practically speaking, we know this doesn't scale, but for simplicity's sake, let's just assume it's fine. So all your images are now in the form of a CSV. So if you were to train, say, a neural network, we can visualize this process as a CSV going into the neural network and predictions coming out. We know that in general, a CSV of data is just a list of features. So there's nothing stopping us then from converting our original CSV of features, which happen to be images, to a new CSV of different features. We call this feature transformation, and you've seen many examples of them in the past, such as RBF kernels, TF-IDF, and so on. Well, in this case, it just so happens that our feature transformer is the VGG network. The key point being, we trust that the VGG network will give us good features, because it has produced state-of-the-art results in the past and has been trained on millions of images. Images are images no matter where they come from, so if they worked with random images on the internet, they'll probably work for my images too. So one way to think of this is, suppose you had two separate scripts. Script number 1 takes your original dataset, which are the images, and applies the VGG transformation, and then saves that data to a new CSV. Script number 2 just runs logistic regression on that new CSV. You could even do that in scikit-learn if you wanted to. One major advantage of transfer learning is when you don't have that much data. We always want to be mindful of our parameter to sample ratio. If you recall, we discussed this way back in linear regression. Generally speaking, we can think of our data as an n by d matrix. This means we have n samples and d input features. So for a linear model, we'll have d parameters. For a more complicated model like a neural network, we'll have many more. But the main idea is, we don't want d to be too big with respect to n. We phrase this as, we want our data matrix to be skinny rather than fat. We want d much less than n. So when it comes to images, suppose we just can't help but have a small number of samples. Well, this is not a problem, because VGG has already been trained on millions of images. And on top of that, by letting VGG do a feature transformation, you are already reducing the dimensionality. So the benefits are twofold. Number 1, it's almost as if you've augmented your dataset with millions of images from ImageNet. And number 2, you reduce the number of parameters so there is less risk of overfitting. And so this is very helpful when you don't have large n. Then one question you might have is, why VGG? We know that deep learning progresses very quickly, and that even just a few years in this field can be considered a long time. VGG came out in 2014. Since then, other models with more layers and more novel architectures have come out. So why don't people just use those? And the simple fact is, VGG just seems to work better. Nobody knows why. In other applications, such as neural style transfer, VGG works great while other networks don't. Of course, when it comes to classification of everyday objects, newer models have already proven that they can achieve better classification performance, but that doesn't extend to other types of tasks. So for many applications, you can expect to see VGG. That is part of the reason why VGG is so special. Not only is it great for transfer learning and classification, it's been widely used for many other tasks, and it performs better than superior classifiers when you try to apply it to new tasks. Of course, because nobody really knows why it's this way, there's no reason someone can't do something like discover a better neural network next week. Deep learning is a rapidly growing field, and new discoveries are being made all the time.